previously we learned that stress concentration factors go to an infinite value when we're dealing with sharply cracked structures. And we learned that there's a need to develop a new parameter that can deal with those infinite values of stress. That new approach is called the stress intensity factor approach, where the stress intensity factor is a parameter which remains finite even in an infinite stress field. Now, to derive this parameter, let's consider the case of a mode 1 sharp crack of a length 2a. So of a length 2a, and in an infinite plate, meaning the plate is infinitely long as well as infinitely wide. Now, if we derive the stress field equations for this specific geometry, we can find the state of stress, sigma x, sigma y, and tau xy, and sigma z, as a function of the distance from the crack tip, r, at an angle of theta. All right, so we can literally calculate what is the state of stress anywhere near the crack or very remotely far away. And these stress field equations are how we do it. All right. Now, with these equations in hand, we can then start to evaluate what is the stress right at the tip of this crack. Now, the stress near the tip of the crack in the y direction, so in the direction of loading, when the angle theta is equal to 0, simplifies as follows, where sigma y at theta equal to 0 is equal to the remote stress times the square root of a, which is half of the crack length, divided by 2 times r, where r is the distance from the crack. We also can separate the numerator and denominator of this, where the numerator is the remote stress times the square root of a, and the denominator is that square root of 2 times r. Now, what's interesting for this sharp crack is as r, and so the angle is 0, as r approaches the crack tip, something interesting occurs. You see, as r approaches 0, our denominator approaches 0, and so the calculated stress we have becomes infinite. It's the same solution we saw in the previous video, where if we have a sharp crack at the crack tip, stress is equal to infinity. The mechanics of materials approach breaks down. However, what if instead of evaluating this in its current form, where stress is equal to this term, what if we rearrange it and try to find a quantity that remains finite, even though stress itself is calculated to be infinite? So if we do that, we could take, say, the denominator on the right-hand side of this and move it over to the left-hand side. If we do that, we end up with the following, where sigma y times the square root of 2 times r is equal to the remote stress times the square root of a, where the remote stress is a finite value, right? It's something we've applied, and a is a finite value. It's half how long our crack is. In that case, both sides of the equal sign remain finite. Rather than exploding into an infinite value, this is a finite value that we can evaluate against. So this basic concept in common practice is this calculated term from our geometry is defined as the stress intensity factor, K, and is written in the following form, where K is equal to sigma times the square root of pi times A, or if we are in the mode 1 of cracking, it's K1 is equal to the same term, where the pi value is added for some numerical reasons. right? Now, it's important to note that this stress intensity factor parameter, this calculation from our geometry, is in the units of megapascal times square meters, or KSI times the square root, of inches, right? And that sigma is our remote stress very far away from our sharp crack. Now, stress intensity factors also exist. The calculations of K also exist for other modes of fracture, which we'll learn a little bit later. But let's substitute in this finite parameter, this K parameter, back into the stress field equations. If we do so, then we can rederive the stress field equations in terms of that K parameter, substituting it in everywhere that it is found. All right. Now, this stress intensity factor, what is this parameter, this new parameter we found? Well, how do we work with it? Well, let's note that the stress intensity factor K is a calculated parameter. It's a function of our geometry, its size, the shape of the crack, and the type of loading that is applied to our geometry. For various loading conditions and different types of geometry, we can rewrite our K equation as follows, where K1 for mode 1 cracking is equal to a beta parameter times the remote stress times the square root of pi times A, where beta is our stress intensity modification factor, which is related to all the geometric differences for different types of geometry. The beta factor carries the differences in geometry, crack shape, and loading conditions. Now, this beta factor can be found a number of ways. In some cases, there are equations that we can use for specific geometries. In other cases, there are tables that we can use for specific geometries. And there are also even charts that we can search through to try to figure out our beta factor for a specific problem. Some of the best sources that exist are kind of these compendium or kind of big books, tomes, that collect the stress intensity factor equations and modifications for many thousands of different types of geometries. There's the classic compendium by Roque and Cartwright, published in 1976, and in the great tome by Murakami, his 5 volumes of stress intensity factors, published in 2001. And these tomes can be very useful if we want to do that analytical solution for classical types of geometries and loading. Now, our textbook also includes a handful of beta value charts for mode 1 cracking and a couple of different geometries. These charts are located in section 512 of our book. So a couple of examples we have here. Say we have a finite width plate loaded in tension with a off-centered crack of a length 2a. Well, this particular geometry, we have a couple of different dimensions. We have what is the distance that it is off center, what is the crack length 2a, and what is the width of the plate. If we know these dimensions, then we can search this chart. If we know the A over D, we can then search up. And if we know the D over B ratio, we can then search over from the corresponding line and find our beta value, right? It's also important for us to remember that in all these cases, we are using the remote stress when we end up calculating that stress intensity factor, right? Now, in that section 512, there's several different geometries and conditions from related to bending, tension in a plate with both a stress concentrator and crack growth, cracking in a pressure vessel that's internally pressurized. There are a number of different scenarios for us to look at. And now finally, let's talk about cracking modes. Now, the stress intensity factor that we derived was related to mode 1 cracking, a condition where we have an opening mode of our crack, where the load we are applying is perpendicular to the crack surface that we are opening. But there are also two other loading modes that we can see. Mode 2 is where we have in-plane shear, where we're shearing in plane to our crack surface. And then mode 3 is out of plane shear, where we are shearing across out of plane of our fracture surface. Now, for each of these loading modes, we have different beta factors that we need to find. And so the calculation of these K values are separate from each other. In addition, the K values themselves in combination can't always just be linearly combined. We can't just add K1 plus K2 plus K3. Sometimes there are weight factors between how they combine with each other. So it's important for us when we get to more advanced problems beyond this class to note that the mode of cracking can have a big impact on fracture in structures.